The big picture in pictures. There is nothing like a memorable picture to speak volumes. These pictures express what we individually may know, and collectively should know. They can help us understand the world within us and around us, and are suitable for framing in your mind, or hanging on the walls of your living quarters. Most of all, they will be your friends once you get to know them. A deeper understanding of these images may lead to a lifetime of research and study. We hope that viewers are inspired according to their own curiosity and aptitude, and find time to explore more. May these images help us understand the grand scheme of the universe and life itself. This is the big picture in pictures. Bang! A supernova has exploded, sending energy, seen and unseen, and new substances into space. The significance of this image being first is that supernovas are where much of our world originates. The lighter elements, including those that are critical to life like carbon, oxygen, and nitrogen, are made in the smaller stars like our Sun. All the other elements heavier than iron are created in supernova explosions as shown here. Either way, it is clear that we are made from stars. Depending on its mass, a star may shine as a nuclear fusion machine for some millions to billions of years, making heavier elements from lighter ones. The most massive stars undergo a violent death when they collapse and explode as supernovas. A supernova is immensely bright, not only to the human eye, but as viewed in higher energy regions of the spectrum. We are no longer limited just to seeing visible light with human eyes, since probes like the Hubble Space Telescope, Chandra X-ray Observatory, and Fermi Gamma Ray Telescope gather the images and bring us useful scientific data from across the whole spectrum. Protons, electrons, quarks. This summary of the Standard Model of elementary particles can only begin to explain the complexities of how these fundamental particles and forces came to be in the beginning, or how they combine to form everything we know about in our local world and the universe far beyond. But the symmetry and simplicity of the Standard Model, like building blocks, is an achievement of beauty from the science of physics. On the top left are elementary bits of matter called quarks that make up the basic atomic nucleus of protons and neutrons. Just below is the electron, whose home is the outer part of the atom. Electrons, of course, enable electricity and electronics. Forces that interact with particles are on the right. Light is represented by the photon. The recently characterized Higgs particle is responsible for the force of gravity, requiring massive instruments to characterize what we experience directly. Upon the Standard Model are built the elements and all of chemistry. What a body of knowledge is incorporated in periodic table of the elements. Columns of elements tend to have similar properties, and it was gaps in early versions of the table that helped predict the eventual discovery of the missing ones. In this one image are organized metals and nonmetals, gases, liquids, and solids. Some of the elements are essential to life like carbon, oxygen, and nitrogen, while others are toxic like lead and cadmium. Here we find the most common elements on Earth, like silicon, combined with oxygen to make rocks and sand. Others in the table are rare, not to mention valuable at the same time, like gold. Even some that don't exist in nature at all and were made in particle accelerators, atom smashers, are listed at the very end. It is expected that the same elements that were made in the stars will be found across the entire universe. We now can map which elements originated in which type of star. The elements of the periodic table are the building blocks of the molecules of life. Key to this is genetic material, deoxyribonucleic acid, DNA, which is in the shape of a dual spiral helix, held loosely together via pairs of nucleotide bases, made of cytosine, C, guanine, G, adenine, A, or thymine, T, in a scheme where A binds to T and G binds to C across the arms of the helix. The double helix is a symbol often found in ancient art, most familiar as two snakes winding around each other, the caduceus. The intelligence in these building blocks is enabled through just a few of the common elements mentioned so far, plus phosphorus. No less fundamental than the periodic table in chemistry is the elucidation of the genetic code in biology. Genetic material uses a code of 3 nitrogen-containing bases in a sequence, codon, to specify one of the amino acids that are the building blocks of proteins. While proteins are again made of the same common elements mentioned so far, plus some sulfur, they can function not only as what we easily recognize as muscle, skin, hair, and internal organs. Within life, the proteins can also function as catalysts to make the chemical factory of metabolism work. The artistry of this chart of genetic codons is powerful, and its circular form may be seen to embody the meditational value of a mandala. Not only has the genetic code been deciphered, but the Human Genome Project has resulted in a basic genetic blueprint for how a human being is made, providing insight into how genetic diseases occur and could be cured. The previous pictures have led from elementary particles to chemicals and the wonder of life and reproduction. The genetic code is put to constant use as we live, grow, and reproduce. DNA is the vehicle, while cell division and replication is the highway upon which life moves. Even a simplified graphic as shown here reveals the complexity involved. Yet we hardly think about it. Mitosis is basic cell division, where a duplicate copy of the original cell is made. Each of the cells retains a copy of the parent cell's same genetic material. Mitosis is used by single-celled organisms and within our own bodies when new cells are formed. The phases of mitosis are shown in this section's image. The genetic material, chromosomes, first begins to duplicate and start separate into two copies. They then form their own separate cell nucleus so that when the cell divides, each copy contains the same genetic material. Sexual reproduction, called meiosis, is different in that the two parent cells' genetic material are copied once, but the cell divides twice so that the offspring cell contains some of each of the parent's genes. A picture of water is next because besides basic organic molecules that make up living things, it's water that enables plant and animal life to thrive in Earth-like fashion. Plants need water along with sunlight to make oxygen, while extracting carbon dioxide from the air into their own growth. With some exceptions, animals including ourselves cannot survive for long without water. One of the first steps in developing any branch of science is to classify what is known. Taxonomy is the term used for biological classification, while phylogeny adds the genetic and evolutionary origins of each species. Shown are three main branches. The diversity of life on Earth is truly amazing. The tree provides perspective on how plants and animals are just small branches of the diversity of life, which extends to microscopic bacteria and archaea. Plants and animals emerge from the far upper right of the chart. The animal kingdom is continued in the next image. Pause to recognize the animals you know. So far we have covered mostly physical and chemical topics that we expect to be very repeatable and predictable. Actually, this is not quite the case, since even quantum particle physics needs to recognize probability in the uncertainty of knowing a particle's location and momentum at the same time. So we continue to the next image you should know, presenting a simple curve, the statistically normal distribution, or Gaussian curve. Engineering makes good use of probability to keep products operating over a wide range of conditions, as do applied sciences like quality control that keep processes running within their expected range of random variations. As every sports enthusiast knows, teams don't often win every game of the season, with a final playoff winner often based on winning a series of, say, 3 out of 5 games. And when it's party time, arriving early puts you on the left side of the arrival curve, while showing up late is on the right, but the average is the middle peak where most attendees arrive. Statistics, uncertainty and probability play into the images we show on these pages and how those principles work in the real world. The next image is about the energy that makes chemistry work, as well as light, heat, and radio, electromagnetism. You can easily visualize a rainbow that shows the spectrum of visible light from red through violet. You can feel the heat of infrared and get sunburned by ultraviolet. Beyond that, the still more powerful X-rays pass through all but the densest parts of your body. And a strong magnetic field holds your souvenir magnets to your refrigerator. Both electric and magnetic field components are shown here in this basic view of electromagnetic fields. Knowledge of how to manipulate and use electromagnetism has had profound impact not only in the advancement of physics, but in applications that include electrical power and electronics from radios and cell phones, to microwave ovens, computers, X-ray imaging, and even space telescopes. James Clerk Maxwell developed much of the basic theory, known as Maxwell's equations, with numerous other contributors followed by those who put the theory into practice. We live in an increasingly electromagnetic world, both wired and wireless, while we have always been surrounded by the electromagnetic influences of the sun and other objects in the sky. Earth itself has a magnetic field, enabling the compass to point north and helping to shield us from many of the harmful effects of the sun's overpowering radiation. What is provided in nature and discovered by science may be used to advantage by human technology. Few inventions have had the impact of solid-state electronics, beginning with the p-n junction that enabled the first transistor. The junction itself is deceptively simple, with a small excess of electrons, negatively charged, or N carriers, on one side, and an absence of electrons, positively charged holes, or P carriers, on the other. From this basic structure and its variants are built diodes, transistors, logic circuits, radios, computers, and practically every other electronic device. Even without high technology, crude p-n junctions also exist in nature, and the curious experimenter can pick up AM radio stations with a crystal radio. The image clearly shows how a potential energy hill is created between the p-type and n-type areas of the junction. This provides an easy way to visualize, without math, how such a junction can be a rectifier, and allow current to flow only in one direction down the energy hill. A simple diode based on a p-n junction can turn alternating current, AC, like the kind coming from a household power outlet, to direct current, DC, like the type of current produced by a battery. This basic structure is also capable of interacting with received light, photons, to generate electricity, thus enabling photovoltaic or solar cells, and in reverse, with electricity provided to it can also directly produce light, enabling light-emitting diodes or LEDs. Add an additional N or P layer contact and the p-n junction becomes a transistor, capable of amplifying signals and a host of other functions we take for granted in our electronic devices. The first transistors were announced in 1947, replicated by the thousands and millions. Similar structures based on the field effect transistor and its variants are the basis of integrated circuit chips, ICs, computers, memories, and so on. This leads us to our next image. Advances in how many of field effect transistor junctions used in computer microchips in the past few decades has followed a predictable growth pattern, Moore's law, which states that the number of transistors in an integrated circuit doubles approximately every 2 years. This is amazing technological and economic progress, enabling the modern information and telecommunications era of personal computers, networks, smartphones, and the World Wide Web. Knowledge that grows exponentially is the key to our future. We take it for granted, but the curve shows the incredible progress that has been made over just a few decades. However, there are limits to this growth, since the dimensions of these devices are getting so incredibly small. As of 2018, the death of Moore's law was being announced as a reality. Some technologists predict that new materials and structures, for example the quantum transistor, spintronics, or graphene, may enable further growth. Our upcoming energy future is clearly going to be harnessing inexhaustible and renewable sources, rather than the use of limited resources and polluting fossil fuels. So the chart of progress in photovoltaic efficiencies, solar cells, is our next image. Here we build on a few related themes already mentioned: the p-n junction, electromagnetic waves, and the periodic table. As we mentioned, photons can interact with the right materials to directly produce electrons. There is no radioactivity involved, no steam generators, no carbon dioxide released, and no waste once the solar cell is put into use. Several families of technology are represented: silicon-based cells, those made of gallium arsenide, cadmium selenide, lead iodide, some made of multiple junctions to improve efficiency, and a list of other emerging materials that hold promise. This chart points to our future if we only take advantage of it. Note that breakthroughs are not the only way to achieve progress, it can be done in small steps as well. You will never get lost if you have this handy pocket map of the universe. Plotted on logarithmic scale, this image compresses the locations of known objects from Earth, across our solar system, and on to the farthest regions of space, all in a single chart. Starting from Earth on the left, you pass the many Earth-orbiting satellites, to the Sun, Moon and planets, then to the edge of our solar system to the Kuiper belt objects including dwarf planet Pluto. Beyond our own Milky Way galaxy lies the local group of galaxies, then basically everything else up to the known edge of spacetime, the cosmic microwave background remaining from the Big Bang. Such a map is significant for what it represents in our reach to understand the vastness of the universe. We acknowledge the brilliant mathematical work of the authors to compress it all to note card size. The graph is quite long because it covers distances over 20 orders of magnitude, powers of 10. So the next 2 pages split it in half to make it easier to see. With room for more detail, what you see, from left to right, are Earth itself. A cloud of artificial satellites orbiting Earth, Earth's moon and sun, inner planets, asteroids and outer planets of our solar system. A gap labeled Oort cloud, which can be thought of as the home of comets. In the next picture, we see the nearest star, labeled Alpha Centauri. Other stars before the end of the disk of our Milky Way galaxy. The local group of next nearest galaxies. The rest of the distant universe. At the far right is the cosmic microwave background radiation remaining from the Big Bang. Our bonus image is not usually associated with science. But the fundamental laws of the universe from which we have just sampled must apply to everyone. How could it be any other way? This final image is offered as a bridge between science and mankind. The coexist graphic incorporates symbols of the major religions of the world. This graphic embodies the merging of humanity's search for truth with the deep symbolism of our sacred signs. Rather than extremes of opinions, it speaks unity for millions and billions. From a common basis in science, we must stop bigotry and violence. We can fit the pieces together to make a world where we can be smarter and get along much better. Our understanding and control of basic physical properties has enabled a new age where we are capable of communicating around the Earth and begin to explore the universe, while beginning to realize how we can use the endless energy all around us. We have some understanding of the codes of life, and how all forms of life are organized and interrelated. Great advances in transportation, communication and medicine continue to enhance our lives. However, most of the capability, even when expressed in pictures, is still so much magic to many of us. Hopefully the graphics presented in this short piece will give you food for thought. Please partake generously. We must continue this journey, and to do so in a way that recognizes our commonality and expresses the best intelligence of humanity. We are all made from the stars and will ultimately return to living in starlight. This has been the Big Picture in Pictures.